Hello everyone, this is Abdeh. I am a technical marketing engineer for the Solutions Engineering Organization at ON Semiconductor. Today, I'm gonna walk you through Strata Developer Studio, which is a secured cloud-connected development software to evaluate reference designs, development kits, and evaluation boards with automatic updates and alerts. Strata benefits are out-of-the-box experience, plug-and-play system. Strata automatically downloads all necessary hardware design files, ability to measure and control different design parameters for customized evaluation, complete platforms collateral such as schematics, layouts, block diagrams, user guides, test reports, datasheets, and many more. Strata consists of three main tabs: Strata Main View. Also, each of the Strata enabled boards had a Documents tab which includes all necessary design files, and there is also a User Interface Control tab where the user can measure and control different design parameters. Strata also won IoT World Best in Show Award. 3 easy steps to obtain Strata. First, download Strata from Strata landing page at www.onsemi.com/strata or from any released Strata boards webpage. Register, then log in. After you log in, you will see Strata main page, which has all of the hardware platforms listed under different categories. You can also filter by category, keyword, and segments. You have your distribution portal tab, which will give you access to the Strata page on any of our distributors. We also have a Strata tour by clicking on the question mark. You can also submit any feedback you may have by clicking on the right top corner. Within Strata main page, you can access all documents and design files for any of the hardware platforms by clicking on Browse Documentation. This will give you access to all design files you may need, such as user guide, test report, bill of materials, CAD files, fabrication, and much more. When ordering one of the physical hardware platforms that are supported by Strata, all you have to do is plug in your hardware platform with the mini USB cable, and this will give you immediate access to the Strata user interface control to measure and control many different design parameters. Next, I'm gonna hand this presentation over to the team to talk about the LED car tail lights.
Hi, this is Eric Beaver here with ON Semiconductor. Today I'm going to walk you through the steps of getting started with the NCV7685 Strata-enabled automotive LED driver evaluation board. The 7685 offers features such as 12 independently controlled PWM channels, variable PWM frequency, current set point via single resistor, and LED diagnostics. It interfaces over a digital I2C bus that has CRC error detection. It has OTP, one-time programmable, and SAM mode, standalone mode configurations for use without a microcontroller. Typical applications include dashboard lighting, rear tail lights, such as this design here, daytime running lights, fog lights, etc. Here's a block diagram for the board. By default, the LEDs are powered off of a USB voltage V-bus. It gets boosted up Alternatively, for higher power applications, you can use an external power supply that gets fed to a bypass load switch or to a buck regulator that can adjust this voltage via the user interface. That voltage gets fed to the LED driver through a current sense resistor to monitor the total LED current. There's also switches and an external LED connector that allow the onboard LEDs to be disabled if the customer wants to use external LEDs for their own application. There's other hardware interfaces such as the comp configuration pin for controlling SAM modes, chip selects, output enable, and iSet via that single resistor. There's other telemetry on the board such as voltages and currents for various things. And there's also temperature readings for the LEDs and then for the LED driver itself. Here's a Strata user interface. By default, this thing powers up in a car demo mode, and it's plug and play right off the bat. So you only have to plug in a single cable, and you immediately start with a functioning evaluation board. The controls here are the hazards, left-right blinkers, brake, and reverse lights, just like a standard rear tail light of a vehicle. You can also manually control the background brightness or automatically if the ambient light sensor is installed. So I'll go ahead and fire up Strata right now. So here's Strata, and here's my evaluation board on my right. It's not plugged in currently. I can open up the Browse Documentation button, and what that does is it'll go up to the cloud and download all of the documentation related to this platform. So here, the schematic loads immediately, and I can see the LED driver and all the LEDs. The entire schematic is on this. There's other things such as the block diagram that we just reviewed, layout files in Gerber format, PDF-wise. If you want to download the source files, you can do that here in the download section. These source files that are developed in Cadence. There's also data sheets for each part that's on this board. So for example, here is the temperature sensor that's being used. This goes and loads from the web, so you have all this information all in one spot. Here's the LED driver. So if you had a question about what exactly is going on with this LED driver, you can just switch over to this tab and review this documentation. So if I close this and come over to my platform and plug it in via the USB cable, Strata will detect this automatically, and it'll show it as connected here in the platform selector. And a new button here is enabled called Open Platform Controls. So I'll go ahead and open that. So right away, by default, this is a functioning UI with a hazard light source, so the UI is being updated from the firmware as the firmware on this board sets the LED states. These buttons on the right can control the status of the lights, so I can disable my hazards, turn on my brake lights, turn on my reverse lights, left blinker, right blinker, or both of them at the same time. There's also a feature of this evaluation board to control the background ambient light manually. So as you can see here, the background got darker by clicking the moon, and our running lights turned on. And if I hit my brake lights, they'll be a little bit brighter. There's a help question mark here. If I click this, it'll go through all of the UI elements and ensure that they're, or just describe to the user that here's how these are the features of the UI, and here's some applicable details. You can use the right and left arrow keys, or you can hit the previous and next buttons. But there's some pretty detailed information here. If the customer has any questions, they can access these help messages, and they should resolve any problems before contacting ON Semiconductor. So the next UI is the LED control tab, and it provides full control over all the register settings of the LED driver, the I2C with the easy to use, intuitive user interface. So there's just general settings such as like output enable, to turn off or on the LED driver, PWM, individual channel configuration, diagnostics, and I2C registers. So we'll switch back over to Strata. So all you have to do is click the LED control tab. It'll configure the LED driver, and right away you can see on the eval board that all of our LEDs are enabled and at a really low brightness. So I'll walk through each of these elements. You can turn off the output enable, and it'll just shut off all the LEDs. You can adjust the current set resistor via digital pot. I can slide this back and forth with my arrow keys, and then you see the brightness of the LED driver getting brighter on the UI, or on the video of the board. I can disable my PWM, and this will make the LEDs way brighter because they're operating at 100% duty cycle. If I turn it back on, I can adjust the duty cycle of a channel. So here, the first LED row on the left, the yellow ones are full brightness and no brightness. I can also lock together the PWM duty cycle. Click this button. Only the first out one channel is adjustable, and if I adjust it, it'll adjust all the channels at once. You can also do the same thing with the enable, so you can lock all the enables of the PWM together, turn this off or on. There's a PWM linear log setting. By default, it's in log mode, so you have a little bit more linear operation of brightness throughout the whole duty cycle range. If you change it to linear, you don't really have too much resolution before the LEDs get way too bright to look at. This is due to the non-linearity of the light intensity of the LEDs. You can also change the PWM frequency. There's 4 different options: 150, 300, 600, and 1200 hertz. If I disable my PWM, there's individual enables for each of these channels. So one by one, I'm turning off all these LEDs, and one by one, turning them all back on. There's a connector at the top of this board, right up here, right above the LEDs. And you can disable these onboard LEDs. So if I disable the first one, you can see it goes off in the video. I'll disable a few of them. I'll disable the first 4. And so now the user can use the header at the top of the board to connect to their own application. I can set my diagnostics to diagnostic only. And you can see here the channels that I have the onboard LED disabled on became a fault status. And you see that with your diag pin interrupt. If I change it to auto retry, all of the LEDs shut off, because in auto retry, it puts all the current, if it detects one fault, it'll put all of the channels in a fault status. If I disable all of my off-board LEDs, so all my onboard LEDs are enabled again, you see my fault status goes away and all of my LEDs come back on. Another thing to mention here is all the status registers. Just like on the car demo mode, if you have any questions about this, you can hit the question mark button, and it'll go through all of the help messages. And it'll go through all of these fault statuses one by one. You can also view the LED driver data sheet to get a little bit more information. Specifically, this diag range, there is a resistor divider off of VLED voltage. If I go back to my documents and open up my schematic, here's my LED driver page. And here, this diag enable pin, there's a divider off of here. And this divider is set to generate a reference here of 2 volts when our input voltage, or VLED input voltage, is 8.5 volts. And that's to detect under voltage events on VLED. I switch back to my control and preliminarily go over my power tab. You can see my boost voltage is set at 9 volts, and you can confirm that here in this reading. If I switch it back to about 8 volts, come to my LED control page, you can see here my diag range is enabled, so it detected an under voltage event on VLED. The next section here is the power, and you already got a brief preview of that, but I'll go through all of these again. But this tab controls the input power supply, whether it's boost, buck, or bypass, as I described in the block diagram. It can also adjust the VLED voltage when you have the buck or boost supplies enabled. And it also monitors telemetry, voltages, currents, temperature, and power. So just click over to my power tab. The first control I see here is VLED input voltage type, and currently it's set to boost, and that's the default. I can reset the VLED voltage by just clicking reset, and you see the LEDs flash off, come back on. And I can adjust this voltage, as I showed previously. I can switch over to different power supplies. If I click bypass, you see here my LEDs turn off, and the reason they turn off is because I don't have an external power supply connected. So VLED voltage dropped almost to 0, and my connector voltage is 0, which is where my banana plugs are on the bottom of the board. So I have an external supply with me, and I'll plug in these banana plugs. I'll turn my external power supply to be at 15 volts, and my LEDs come back on. Now you see my connector voltage is 15, my LED voltage is 15. And I'm in bypass mode. I can change over to buck mode. My buck's set at 9 volts, so it's bucking down the 15 volts of VCon to 9 volts VLED. There's other telemetry, such as the iLED current. So this is the global current going through all of the LEDs, 10 milliamps. Here's the VS supply of the LED driver for the digital interface and all of the analog pins that are associated with the LED driver. And the supply current for that is also monitored at 4.2 milliamps. The reference output, this is a 3.3 volt reference output out of the LED driver, and it can power other sensors. And then there's also VDD voltage, which is the digital interface voltage. There's other fault indicators down here. If I change back to my boost setting, my boost input current is limited from my V-bus rail of the USB. So if I try to turn my PWM enable off and reset or increase my ISET limit, you see here that my LEDs turn off, and I get a warning here in my power tab. It's a continuous warning. And that's trying to restart the boost regulator, but it can't because the current is too high. So if I come back over here to my ISET and lower my current back down to 6 milliamps and click reset VLED, I might need to lower it a little bit more and potentially turn PWM on. Click reset again, and you see my LEDs come back on. So it's just because there's a power limitation on the USB line. And there's other things for thermal warning and thermal shutdown. If this device gets too hot, it'll let you know via the I2C interface. There's also temperature readings of both the LED driver and the LEDs and a total power. A neat feature of this is if you wanted to use a buck regulator, you could dramatically increase the efficiency of this LED driver. So if I change back to the buck mode, I'm bucking from 15 down to 9. If I come over to my LED driver tab, turn my PWM enable off, and set my current pretty high for all the channels, the LEDs are quite bright. On the power tab, you can see here I'm dissipating 3.94 watts. If instead of my buck rail, I just bypass that entirely and use the 15 volts in, see here my power loss almost doubles and my LED driver temperature is increasing. Switch back to buck, the power loss dramatically reduces. The next tab is the SAM, OTP, and CRC. SAM stands for Standalone Mode. OTP stands for One-Time Programmable, also known as ZAP in the datasheet. And also Cyclical Redundancy Check is what CRC stands for. I'll go through all those one by one in the UI. Let me go ahead and turn my PWM on and drop my current back down so those LEDs are a little bit easier to look at. The first control here is I2C CRC. that can be turned on. This is pretty transparent to the user. You'd have to have an I2C analyzer or an oscilloscope to see the extra frames that it's inserting into the I2C communication. The CRC enables, well, it ensures that the data being sent to the LED driver and received by the master device is accurate, so it's a double checking mechanism, a redundancy check. So I could also change the slave address. I'll enter a new slave address here and apply, and then that changes my current I2C address to 61. And with CRC enabled and my current I2C address 61, if I close this platform and then open up a new one, I'll get this pop-up menu that says I2C communication with the LED driver has failed. And it's because we changed those settings. So if I change the address back to 61 and CRC on and hit continue, the UI will start up as normal. Going back to the SAM, OTP, and CRC tab, there's another mode here called Standalone Mode. And currently it's in I2C, so all of the registers are controlled via I2C. If I change the mode to SAM, all of the LEDs turn off, and that's because the SAM configuration is set to be SAM1 mode, and the SAM config for SAM1 mode is all off on the LEDs. So if I turn on just the white LEDs for SAM1 and turn off the white LEDs here on SAM2, I could toggle back and forth, and you can see the SAM mode changing. If I change back to I2C mode and then hit VDD voltage disconnect, this will actually put the LED driver back into SAM mode because it lost VDD. And if I reconnect, it'll put it back into I2C mode. If it's in SAM mode, you can also set the open load diagnostic specifically for SAM mode. If you want to configure all of these settings to be OTP'd, the CRC, the address, the mode, all of the SAM configurations, you can click one-time program or ZAP. A pop-up will come here that says that the part will be permanently OTP'd. So don't do this unless you really want to do it. This part in particular has not been OTP'd. So we'll go ahead and hit continue here, and I'll show you the side effects of doing that. So hit continue. And what I'll do is I'll completely unplug the board from all power sources. So the board has no power connected whatsoever. I'll plug the USB connector back in. So we get that same message right here, and we got that message previously, but it's because we didn't power down the board. If we would have powered down the board and then restarted it, it would have reset the address and the CRC back to the non-OTP state, the default configuration. But now, since we powered cycled this and it's in non-volatile memory, we have to do this manually every time from here on out with this board. We'll go back to the SAM, OTP, and CRC tab. So if you go and OTP it again, or try to OTP it again, it'll ask you if you want to OTP it, and you can continue. And it'll say that it can't be OTP because it was previously OTP'd. And that's what it does is it goes and looks at all the register values and the OTP registers, compares them to the default value, and if they're different, then it says it's been OTP'd. So we can click continue now. And just like all the other tabs, there's help messages on all these. So go ahead and look through them if you're confused about what control does or how it operates. And there's another miscellaneous tab over here that has some default register value from the ID versions, and also some channel errors. So if one of the external LEDs overcurrent limits or something like that, there's load switches on there that'll catch that. And you'll get a little badge up here just like you saw in the power tab. So that's about it on this board. And this evaluation board and accompanying user interface will allow for quick testing and exploration of the features and capabilities of the NCV7685 LED driver. For more information regarding this part or to order the evaluation board, contact us at onsemi.com and browse for LED drivers by clicking on products, power management, and then LED driver section. Thanks for your time. Bye.